So we are live now. Hello, everyone. Today we are going to have a presentation of Jessica. She will talk about Lagrangian and Noether's theorem. And so thank you so much, Jessica. You can present.
Hello, today I'm going to present about the Lagrangian formulation of mechanics and the Noether's theorem. So, first I'll make an introduction about the Lagrangian, but I'll be very quick because the Noether's theorem is the most important part of this presentation. It is genius. The Noether's theorem is very special. I'll show when I'm present about. But first, what is the Lagrangian? Lagrangian is a compact way to describe the dynamics of a system, of a physical system. Instead of using forces, normal forces from Newton's laws, for example, the second laws of Newton, we use energy. So the Lagrangian is the difference between the kinetic energy and potential energy. And it is very important for particle physics because we can, for example, simplify the description of the systems in too many particles. If we had too many particles and we were to find the force of every single particle, it would be very tedious. It would be a very long job. So using energy, we don't have to worry about vectors. Okay, for example, can we use the Lagrangian on a pendulum? Yes, to describe the movement of the pendulum. This T here, for conceptualizing with the other newer students that are here, T stands for kinetic energy and V for potential energy. Here we are having, here the sign was positive, but it depends on the reference we're using.
So just adjust the screen for the YouTube.
Okay. We could use also the Lagrangian to describe the motion in something similar to a roller coaster, that it is very similar to a function. The shape of the roller coaster being the function and those people here being the particles, for example, if we are analyzing. So depending on how the particles are moving on this function, they are constrained, they are fixed to move in this function. So we have the Lagrangian for it. And if we need, for example, to find the equations of motion, normal ones that we use on classical mechanics, we do need to put this Lagrangian. We will need to put this Lagrangian on Euler's Lagrangian formulation, so we find the equations of motion. Here, very huge is the Lagrangian, and does it obey Newton's laws? Yes, we deduce it from Newton's laws using variation calculus. I won't deduce here because it would be very boring. So if we take classical determination of what the kinetic energy is, what the potential energy is, we find just the second Newton's laws, which is the force is the ratio in time of the momentum. Now, for the most important part, the Noether's theorem. Amy Noether here, yes, she's a woman. She made this theorem of symmetry leading to conservation. And even Einstein, it's true, Einstein recognized her work as something very special. So treat it like very special. It deserves it. She deserves respect. Well, what does the Noether's theorem say? If the Lagrangian of a system, if we find the Lagrangian of a system and it remains unchanged under a continuous transformation, like if we have the Lagrangian of a system here, I will show it, explain more better, a example of it But if we change it some way, it could be translational symmetry. If changes the position, it could be it could be rotational symmetry. If we rotate the system, it could be time symmetry. If the time passes but the Lagrangian stays the same, because remember, Lagrangian is for time. We are using time, no time energy. We are using energy to describe our system. Then, if those symmetry, if it is unchanged, if the Lagrangian remains unchanged, then we have a quantity that is conserved. For example, if I throw a ball and this ball has constant velocity, then we throw that ball again in other space, other point of the space, then we have spatial translational symmetry. I will show a better example, a video. I hope it loaded here on Canva, but I think yes. I will show it is better to see. So we throw the ball is moving, constant velocity, no acceleration. We move in a space, we throw the ball again, and the ball moves in the same way so that the Lagrangian doesn't change. That's translational symmetry that we have here. We have another type of symmetry that is rotational symmetry. We, again, throw the ball, and if we were to rotate the space, we throw the ball again, and yes, the Lagrangian remains the same. That's rotational symmetry. And for time symmetry, we do it and we do it again, and it happens the same thing. Okay, so Noether's theorem says that every differentiable symmetry of physical systems corresponds to a conservation law. But can you show us a better example of what it is? Oh, because I talk about the ball, but what does it mean physically? Okay, I put this slide in another order here, but I will show this part first, and then I'll come back to the Noether's equation. So the first part here stands for conservation of momentum, that is translational symmetry, and for rotational symmetry we have conservation of angular momentum. For time we have conservation of energy, and we have also gauge symmetry for, I think someone wants to enter the meeting, but I'll continue presenting. And we have electric charge symmetry that it stays the same. So I came back, to the equations, but it'll be very quickly because it could be scary for someone. So L stands for the Lagrangian, and if we put those terms, we expand those terms. Here is the variation of momentum, which means force. We obtain the quantity that is conserved. And for this system here, the quantity that is conserved for the translational is momentum, rotational. Okay, but I think this is the better example I can show you because it is mind-blowing. When we have here the space shift, it is going up, and we have the action-reaction pair, that could be seen as a symmetry. And that is very cool because it looks at the Newton's laws in a different way. Okay, so the Noether's theorem is very, very important. It explains a very huge part of physics that is for conservation of energy, conservation of momentum, and some other things. And it is very important to me also for the standard model, which is for particles. But does the Noether's theorem remains the same if we had a very huge time if I say the time is very huge. The variation of time is very huge. Doesn't Noether's theorem remains unchanged because the space, I mean, it is losing energy. How can it be conserved if the energy of the universe is changing? It isn't conserved. So, well, that's a problem, but not a very huge problem. It's just for long periods of time. Imagine if we had, for example, it could be, oops, it could be confusing. For example, if we had rotating system, we see the ball as we were outside, and we see that that same ball inside, it moves differently, but not really. It doesn't move differently. It depends on the reference system we are using. So, for example, if we analyze the Lagrangian of our system, it could on different things because we are using different references. That difference means that the symmetry is changed? No, not really. And we use, for example, forces to, I think, put this in equilibrium. For example, if we had a plane, this plane is traveling, and then we do the Lagrangian based on the amplitude. For example, we are at the level of sea, and then we are in a level mountain. The amplitude, the altitude that the plane is changes. The amplitude of the plane is changing? No, not really. So we add a fictitious force to explain it, but it's just a matter of reference. So, in conclusion, the Noether's theorem, yes, it is very important for physics. It describes a lot of how energy and symmetry works, how momentum, how charge conservation. It is very important. So that's my presentation. Thanks. Questions?
Thank you very much.
Se prepara.
Thank you, guys.
Boa tarde, pessoal. Boa tarde a todos vocês. Nós temos algumas duas hosts novos, né?